There we go. Okay. So anyway, we'll talk here in a moment about the Canvas where you can find your packet again. I just want to get started with the notes for those that are already on and whatnot. All righty, let's get this going. So up to this point, chemists, we've talked about one particular model, and that is Rutherford's nuclear model. All right, Rutherford's nuclear model. And so I'm going to write that down. We have Rutherford right here, and his model was the nuclear model. So he had our nucleus, which had protons and neutrons in it. And then outside that nucleus, just wherever, were the electrons. We found out that there's a lot of empty space in the atom, that it had a nucleus. That's what the nuclear model introduced through his gold foil experiment. And that's kind of where we stopped and what we were looking at. But there was a lot of stuff that actually Rutherford's model, sorry, I'm changing the color of my pen, that Rutherford's model did not explain, and it happened to be with the electrons. So that's what this unit's about. It's about what's going on with the electrons in the atom, and then we'll also focus on the nucleus. So we're going to focus on the outside of the atom and then also the inside of the atom. So Rutherford's model did not explain electron arrangement, which is really their location, and motion. Electron arrangement and motion. It did not explain that. We didn't know what those electrons were doing. We thought they were just kind of floating around out there, moving fast. He didn't really ever say anything about them. The other thing that's weird is that he did talk about why the negative electrons aren't attracting the positive nucleus. Because when you have positives and negatives, these are opposites. And what they do is they attract. They attract, okay? Opposites attract. So according to his model of the atom, if I have positive here and I have negative here, what those two should do is attract to one another. And that would then pull them in together, and the atom should collapse. But it doesn't. Obviously, it doesn't. Our atoms right now are not collapsing. And there is a positive nucleus and a negative outside. So then the question becomes, why? What's going on? All right. So Rutherford didn't explain a lot. So we're going to move on to Bohr's model and a few other models today and into tomorrow and Wednesday. But in order for us to talk about really what's going on with the electrons, we have to review a little bit on electromagnetic radiation. EM radiation, EM stands for electromagnetic. If you want to write that down, you can. You don't necessarily have to, though. EM radiation is obviously energy that travels in waves. That travels in waves at the speed of light through space. It doesn't matter what type of electromagnetic radiation you have, it all travels at the speed of light through space. Now, the other cool thing about EM radiation is it also acts like a particle. We've used this word particle before. We've used particle when we talk about protons, neutrons, and electrons. Those are particles. And EM radiation also act like a particle, which we call a photon. A photon is like a packet of energy. A packet of energy. So there are many, many, many types of electromagnetic radiation. And so here's why, you guys, I put the notes in the packet together. And for those of you that are writing with pencil and paper, totally fine. But some of these visuals or diagrams, you can always go back to Canvas to look at those instead of drawing them on your paper. That might be kind of challenging. So just be aware, if you're taking notes on your paper, totally fine. But I have some of these diagrams in the packet in Canvas in case you want to go back to them to review. So here's our levels of electromagnetic radiation. We have gamma, and you've maybe heard of gamma, like with the Incredible Hulk, green monster, right? He had gamma rays, which made him get all green and crazy. X-rays, if you've ever had an X-ray, there's that. Ultraviolet, that's the same as UV, which we get from the sun. Visible light, which can also break out into the colors that you see there. Infrared, similar to thermal or heat. Microwaves, and then your lovely cell phones use radio waves. So we have all of these levels of electromagnetic radiation. And this electromagnetic radiation has various levels of energy or force, I guess is maybe a word you could use too. It all travels the speed of light, but some are just more extremely energized than others. And where we know this or can see this is based on what they can do. For example, gamma will go all the way through our body, penetrate our bones, our cells, our tissues, and go straight through us. It's incredibly intense and dangerous to us. X-rays, if you have it in too much of a dose, can be dangerous to us as well, which is why we wear that lead vest over us when we get X-rays on our teeth. It can penetrate through tissues, just the bone. It will allow us to see that bone. And then ultraviolet, same thing as skin. That's where we get our skin cancer. So obviously all of these have energy and can have a massive, effect on us. And absolutely, someone just said, hey, my Wi-Fi's glitchy and I can't hear you very well. I'm recording this lesson, so you will be able to watch it later too, you guys, if it's glitching out. So no need to panic. So then we go down to visible light, infrared, microwave, and radio. So this is very low energy stuff. Oh, my pen's not working. This is very low energy. And this is very high energy. Woo. Everything's breaking down today. Try it again. There we go. High energy. Okay. Now, notice the wave we have here. The wave. Down here, we have a very, very long wave. Okay. It is much longer. And over here, we have a very much shorter wave, right? Now, if I were to pick up this guy right here and move it, you could see that in that amount of time, let's say I made that 1 second of time. If this were 1 second of time, I only got one wave in, okay? But if this were 1 second of time, I got one wave, two waves, and a half, 2.5 waves in there. We call that frequency, how often the wave occurs. So as your wavelength or how long your wave gets longer or shorter, how often your waves happen can change. And then ultimately that affects energy. So down here on your notes, this is kind of the key for those of you writing in your on your paper. And energy, when it increases, the wave's frequency will increase. In other words, how often it occurs. So if you want to write that down, how often it occurs increases, and the wavelength will get lower. So if you go, this wave is more frequent. So look at how short it is compared to like this wave. Less frequent, obviously, is longer. If the energy decreases, your frequency also decreases. So those are directly connected, but your wavelength will increase. So as your energy, sorry, I got distracted. Bradley was saying I need a new pen, and he's right, I do need a new pen. As your frequency decreases, your wavelength will increase. So looking at this, you can see this guy has a long wave, so it does not occur as frequently. Now, you're probably thinking, okay, Hughes, what does any of this have to do with chemistry? Well, in order for us to study electrons, which we can't see, we actually are going to use electromagnetic radiation in the study of these electrons. So to study the atom, we are going to focus, though, on light, not gamma or X-ray or ultraviolet or infrared or microwave or radio, because light is the only one we can see. And that is why, because we can see it. And the light waves, when their frequency changes and when their wavelength changes, that's going to tell us something about energy. So that's kind of what the big ideas are here. If you have a lot of energy, you have a high frequency and your wavelength changes. If you decrease in energy, you have low frequency and your wavelength changes. And so we can see that legitimately with colors. So which light has more energy and why? Go ahead and throw in the chat which color of light has more energy and why. Which one has more energy? Go ahead and throw that in the chat. Awesome. You guys are catching on. So when we look at light energy, which one that has the most energy is definitely purple. I saw a lot of you guys write purple down. That's fantastic. And you're correct. Purple has the highest energy. And then we move down to lower with our red. All right. Now, maybe some of you guys have heard of Roy G. Biv. Sometimes that helps remember things. You have your red, orange, yellow, green, blue, and sometimes we do indigo and then violet. If you've watched Mickey Mouse Clubhouse, if any of you guys are Mickey Mouse Clubhouse, when you were little, watch that. Mickey Mouse Clubhouse, hot diggity dog, hot diggity dog. He actually has an awesome rainbow song that helps you remember. It's like red, orange, yellow, green, blue. Don't forget there's purple too. I'm a terrible singer. I probably should not have done that. But that's how I remember Roy G. Biv is from good old Mickey. He helps out. But for those of you that were explaining the purple, you're right. Purple has a very high frequency. He has a high frequency, which means he has a short wavelength. When these properties of the waves change, they change the energy. High frequency and short wavelength means high energy. Now, as you go down, notice the wavelength gets longer and longer and longer. This is a low frequency, which means low energy. And so red, if you see red, that color tells you you have less energy. If you see purple, that color tells you you have more energy. So the colors of light we see can tell us the energy that electrons are releasing, okay? And that's where we're gonna transition now into the simulation, and we're gonna come back to these notes and we'll tie them together to electrons on Wednesday when we meet, all right? So what I need you to do now is to, if you have not yet, I need to change my screen. Go back to Canvas. And some of you have already done this, some of you haven't, which is why I'm showing you again. It's not the 12th, my bad, you guys. Thanks, Sophia, for making me aware of that. It is actually the 19th, but all of this is correct. I just need to change the dates. I have like 2 classes and I always forget to do something on one of the classes in Canvas. So as you can see today, notes EM waves, which we already did, short and sweet, you're welcome. And then the electron simulation. And you need to click on, oh gosh, Asher, tell me it's not snowing. I don't even want to look outside right now. Sadness. I'm not ready for the snow. Okay, and then here's where you go. Oh goodness, no. 2020, you guys. It's not November yet. We don't need any snow. I'm gonna cry. No, I won't cry. That'd be awkward. Okay, so then you go here and we can open up the packet. And I'm doing this in case you weren't here when I did this. And then I click this link to open it up. And we're going to the electron simulation, which is slide 3. And this will shoot me right to that simulation. And this is where all of us should be. I'm going to get you guys started on this since we have some time in class. And I'm going to make this bigger so I can see it. All right. So in order to do this simulation, we're going to go to this website, and that's going to pop up in another link for me. So I'm going to click this website, go to tinyurl, and that should bring up this lovely website here. And so where that was on the pink, if you click the pink, and then that'll bring that to the website. And I think we'll have time to kind of go through these first ones together, and then I'll let you do the changes in energy and show you how to do that. So this first one says, label the diagram on the left. That's this diagram right here with excited and ground state by dragging the arrows to the appropriate spot. I'm going to make sure I don't want to mess this completely up, so I'm going to do this in my teacher copy. Make that bigger, 100. Okay, so if I go back to this lovely simulation, notice the key up here, you guys, up at the top. Ground state is the solid, excited state is the dashed, okay? So on here, these dashed lines mean the electron is in excited state. This solid line down here where my lovely little E electron, isn't he cute? Down at the bottom is in the ground state. So I'm gonna move these lovely arrows. Oh, that's the ground state. And then I'm gonna move this guy. Oh, and you should also be doing this to one of these dotted lines. It doesn't matter which one. That's the excited state. Okay, so all these dashed lines equal the excited state, and then the bottom one equals the ground state. And you might be thinking, what the heck are the excited and the ground state? You will find out, just not yet. Okay, now it says add the first large energy bar to your diagram and then hit excite. So this is what it will look like, but let's do this. So on a Chromebook, I will tell you it's really challenging to pick it up and drop it. So notice how on my screen right now, I have a hand and then I have the cursor. The hand needs to pop up. If your hand's not popping up, refresh this simulation, refresh it, and then you'll be able to get the hand to pop up. And I got to pull it over, pick it up, and then set it down. Sometimes if you don't do it just right, here, I'll show you what happens if you don't do it just right. It goes back like that. It'll like fly back if you don't get it just right. See, I gotta, there, now I got it there. Once you get him there, the directions says draw the large energy bar and then hit excite. So excite is this button right here up in the yellow. Oh, someone's chatting me. Let me see what they're saying. Chat. Yeah, so this will be assignment, Plamelody. By tomorrow, you need to submit it. So I'm just kind of getting you guys started, and then I'll shoot you loose and get off the Zoom, okay? I just want to show you what it looks like. So I'm going to hit excite. Boom! Oh, look at my cute little electron. Oh, now what's my electron doing? Craziness. Reset. Drag this over. Let's try that again. Excite. Boom. There he goes. Oh, he didn't stay up there very long. Huh. I'm going to do that one more time. You can hit this guy to refresh, or you can just hit excite again. Boom. Oh. Craziness. All right, notice something's happening here as well. That's titled energy, and I'll hit excite again. Oh, crazy. So if I go back to my simulation, here's your questions you can now answer. Add the first energy bar. What happens immediately to the atom after I hit excite? What happens immediately to the atom? And then what happened after a few seconds? And why do you think so? And then what do you think is the difference between ground state and excited state for the atom based on what we just did? So again, let's come back here. I hit excite. Oh, you guys, what do these bars represent? What do these bars represent? Throw it in the chat. What are the bars simulating? Excellent. Yeah, they simulate energy. So let me show you if I put this little energy bar over here and hit excite. Oh, insufficient energy? What? And I gotta try again. So let me stack one on top and hit excite. Oh, insufficient energy? What? Yeah, so these bars represent energy, but you've got to have enough, yay, to get that up there. So the reason I'm showing you that is because you can actually stack the bars too to add more energy as you go about that. And that is what you are going to do for the second part. So I'll need you to answer A, B, and C based on your observations. Do the best that you can. And then in the second part, which you will do without me, you are on the simulation going to try various levels of energy. You will drag these bars over to show how much energy you did for each of them. And then you'll show where the electron went. And this is all in the directions. You'll do it for trial 1, trial 2, and trial 3. And then when you do those, you guys, you also will look at the wave. And you can draw on this document as well. I tell you how to do that. You'll go up to the Insert tab, and you'll go down to Line, and then Scribble. And then you can actually draw waves on here as well in whatever. And this is all in the directions, my friends. Once you have that done, then you'll answer 1, 2, and 3, and that's due at 4 p.m. tomorrow. So that's all you have to do today and tomorrow. And then we'll discuss this, you guys, in class on Wednesday and do a little bit of notes to make it understandable. So my friends, if you don't have any questions and you want to get off and just work on this or take a little break before your next class, you are welcome to do that. And again, for those of you that missed the quiz Friday, send me an email and then I'll get you connected taking that quiz. That's it. Unless you have a question about what to do on the simulation. All right. Oh, how do you make the slide bigger, bud? You go over here to the left, the zoom. You can make it up to 200%, 100%. So you can make it a lot bigger over there. Did that help, Bradley? Or are you talking about when you're in here? You got to click on this electron nuclear packet to make it blow up and get it out there. Did that help? Any other questions, you guys?
Yeah, Miss Hughes, I had a question about the because I'm gonna retake the atom quiz. I'm pretty sure I turned all my stuff. You said something about zeros. That's why I'm just asking a question about that.
So in Power School, if you don't have any zeros, then you're good there. So you don't have to do anything to prepare before Friday. And then you just got to come on Friday, and then I'm going to go through some review on it and answer questions and figure out what's best. And then you guys will have one thing you'll have to do to kind of get ready for the retake, and then we'll be able to retake it.
Okay, and do you have I know Quizlet helps, but do you have anything else that could review that really help? Just for I'm pretty sure I struggled on the atoms, identifying which each element was.
Yeah. Yeah, there's a ton of extra practice. The stuff I provided might have been almost so overwhelming that I gave so many actions that I think kids were like, whoa. So I'm going to have you guys do one of the quizzes that will break down so you can see where you're struggling and do some reflection on that. And then I'll have some extra practice in addition too. Okay?
Okay, thank you.
You bet. Basher, when you retake I don't really have a good way to do that online. Let me think about that actually, on how to do that, especially with an online version. This is something new for me as far as giving online stuff, because I'm so pencil and paper. That's what I'm used to. So yeah, let me think about that, how I would go about you guys seeing what you missed and that kind of stuff. I need to kind of reflect on how to go about that and get back to you, okay? That's a legit question though. So right now you can work on this electron simulation, which is not due until Thursday, or you can take off and get ready for your next class. So this is due Thursday. So based on the, what do you call it? Daily, you can get back to it here as well to go to the electron simulation later if you want to your unit packet if you want to take a break. Sounds good. See you. All right, let's see. I'm going to stop my share